A very good evening to e- a very good evening to everyone who has joined in today with us. And I hope everyone is feeling comfortable back home as we kick things off for the second workshop for AI-driven Sri Lanka. On the second iteration out of 4 of the pre-bootcamp series, we are going to dive into deep learning, for which I hope you, ladies and gentlemen, are excited for. So feel free to post your questions on the Slido platform, whose link will be shared in the Zoom chat shortly. These questions will be directed to the speaker once the session has been conducted. Until then, ensure that you are muted at all times and your video is turned off so as to not disturb the smooth flow of the session. And with that, let's get started on today's proceedings. I would like to invite a speaker for the evening, Mr. Thirunayan Dinesh Jeeva, who is a data scientist and AI-driven lead at Root Code Labs, Root Code AI. He has a master's degree in enterprise application development. His personal research interests include deep learning-based source code analysis, computer vision, optimization, language understanding, and generative modeling. And also, he discovered his interest in AI through mathematics, computer science, and neuroscience. So it's a pleasure to have you with us this evening. I would like to now hand it over to our speaker. So over to you, Mr. Thirunayan.
Hi everyone. Hopefully you guys can hear me. All right, okay. Just let me know if you can't hear me at any point.
We can hear you, sir.
Cool. All right, give me a second. I'll share my screen. Right. Hope you can see my screen too.
Yes, sir, your screen is visible.
All right, cool. All right then. So first of all, hi everyone. Hope you guys are having a great Saturday evening. So yeah, so let's start on with deep learning. So we'll first go through a bit on what we are going to cover in this session. So before starting on deep learning, and we'll try to get to how we as a community or like a research community ended up in deep learning. So we'll go through a short history of intelligence and AI and so on. And we'll then clear the cloud about AI and ML because there's some confusion about, machine learning, deep learning and AI. We'll talk a bit about those. Then we'll dive straight into the deep learning fundamentals. Then we'll look at how we can apply deep learning to different types of data, like computer vision or languages or sequential data. Then we'll go into some new frontiers in deep learning, which are coming up pretty popular recently. And finally, we'll have a fun mythbuster session where we talk about some common myths about deep learning. So about me, I think the host gave a really good introduction. I'm Thiru. I am a data scientist at Root Code. I'm currently leading the AI division. So my personal interests include a lot of math and physics, but I won't bore you with the math today. I can assure you that. All right, so let's start with how we came about deep learning. We'll go through a short history of how we discovered this. So humans, so we have always been dreaming of intelligent machines, right? Actually, for a very long period of time. So an interesting story or an interesting example here is the story of Telos from the Greek mythology. So Telos was this giant machine made of bronze used to protect a princess called Europa. But the interesting part of the story is that this machine was described, around in 400 BC to behave like a human. It was told to have mechanical parts and it can, roam around and, identify potential threats and eliminate it. This is not in any way related to our talk today or modern AI, but it's a good proof that we as humans, we have always been wondering about intelligent machines and how they operate. So fast forward 2000 years, we have two neuroscientists called McCulloch and Pitts, who wanted to try to understand how neurons in the human brain learn and work. So basically, neurons are the fundamental nerve cells in our brain, which are the reason for all brain activity we have. So their idea was basically, if they could mathematically formulate how these neurons worked, then they thought they would be able to easily build a similar connector system which can somewhat simulate the brain, right? So they went on with their research, and they found some really interesting results. First, they identified that neurons work in groups. So for example, if you see a cat, uh, or if you see different types of cats, there are a set of neurons in your brain that become highly active for that visual stimuli. Not the entire neural network inside your brain, only a part of it. So this entire network has certain sets of neurons which become active for certain stimuli. So what you see on the left is an MRI scan showing brain activity in different regions of the brain. And on the right is the mathematical function which they came up with, which said that a neuron can receive inputs from multiple other neurons, and it kind of does this electronical mapping of, of deciding what action should be made next, and that's passed on to the next neuron, right? We'll talk more deeper into how these neurons correlate with what we are currently doing in deep learning later on too, but this is the basic idea. Fast forward another decade, the field of computing was also evolving, and there was very high interest in the area of building intelligent machines too. So a bunch of researchers who were interested in this concept of building intelligent machines came together in 1952. They coined the term artificial intelligence to officially bring it on as a field. So they were excited. So they were like, we have a good mathematical understanding of biological neurons. We have huge computers. We have a bunch of cool people working on it. What else do we need? So they were like, let's go ahead and change the world with AI. So what happened was these guys were too excited to the point where they promised that they would achieve human level intelligence in AI within like 5 to 10 years, and that's in like the 50s. So something like in this first image, where they were expecting very intelligent systems that can perceive and that can move around and even represent parts of human intelligence. Then this happened. So what happened was, they were over ambitious to the point where of using the concepts of biological neurons and translating them into artificial intelligence systems. They weren't able to do it. So for the next 10 years, they were not able to build any system which they thought would be possible. And what happened was there came this period of AI winter, or deep learning winter, where there was no research on AI and especially neural networks happening. And then for neural networks especially, it got so bad to the point where people didn't even mention words like deep learning in their research work. So there was this a bit of a long period of stagnancy in deep learning research. And then during, I think, 89, during, I think, the peak of this winter period, there was an algorithm called convolutional neural network, which we'll also look at in this talk, which was developed. So a CNN is basically a type of a neural network which can identify and understand patterns from unstructured image data. So what you see in this example is basically, a computer is being fed with a raw image of numbers printed on it, and it's able to, it can extract, the numbers presented on it digitally. And then you would have heard of the MNIST data set too. So that's where the whole idea came from. And this led to the first useful application of deep learning in practice. But then it still took many years for us to, grow that compute power to use these algorithms effectively. Fast forward to 2022, deep learning is everywhere, starting from recommendation systems like YouTube and TikTok, which decide the type of content we consume, to personal assistants like Siri and Alexa, and those are just examples of what we interact with daily with deep learning. Uh, even on industry use cases, biotech firms like Pfizer use deep learning to predict protein structures and help them discover new drugs and so on. And obviously, autonomous vehicles and modern computer vision is completely based on deep learning. So how did this happen? How did a concept and technology that was nearly abandoned in the mid-90s is now one of the most powerful concepts within whole of AI? Uh, how did that transformation happen? There are three major factors that played a role in this massive growth of deep learning. First, it's data. And compute power, and then tools, and they're all related. So interestingly, from the 90s, over the past 20 to 30 years, we had developed this exponential growth in computing power, due to concepts like Moore's law and so on. So especially in technologies like GPU, which are capable of doing large number of computations parallelly. And then what happened was we started gathering vast amounts of data too. Because of the internet, this information became widely accessible and more shareable. So these two were the fundamental reasons. And then what happened was, initially, when the foundations of deep learning were being developed, there were only a very few people who could program neural networks, and it was extremely difficult to do so. So over time, we developed these tools like TensorFlow and PyTorch, which has made the technology widely accessible to a large number of users. So all three of these combined, we now have deep learning as it currently is. All right, so now we've been throwing a lot of jargon. I think we've been talking about AI, machine learning, and deep learning. So before we get into the depth of what deep learning is, what neural networks are, let's clear the cloud a little bit. So we'll go through what machine learning is first of all, and then we'll branch from there to deep learning. All right, so this is basically the answer to our initial question. AI is any program, or artificial intelligence is any program that can seemingly resemble human intelligence or decision making. Sometimes AI programs developed even through classical rule-based algorithms can resemble the same type of decision making. So that's a pretty large term. That's the whole, the external circle of that Venn diagram. And then we have machine learning. So machine learning, on the other hand, is a subset of AI, which focuses on learning patterns on data given the right set of features. And we look into what features are and what the word features means also later on. So basically what deep learning suggests is that we have in classical algorithms, we have a set of data and we build the rules. And we build the structured rule by rule instructions on as layers. And the computer executes these instructions. That's where classical algorithms stand. In machine learning, the concept is we provide in data and labels. There's a type of machine learning called unsupervised learning where we don't use labels too, but just for the sake of now, where we feed in data and labels, and we train a model or mathematically a function that can learn to answer, or that can learn to sort of identify the rules on its own and then provide us with the answer. So that's the basic idea, behind the difference between classical algorithms and machine learning. Now, deep learning, which is our topic, utilizes a specific class of algorithms called neural networks to learn from data without, without using defined features. So features is the key word here. That's the major difference between machine learning and deep learning. So data science is not a focus of this talk, but just to be complete, data science is an intersection of all these fields which focus on, using and applying available data to solve problems and deduce answers. So it's a combination of ideas like statistics and visualization to even data analysis. All right. So, like we discussed early on, if we have to understand the difference between machine learning and deep learning, we have to understand what feature engineering is. So, the classical machine learning philosophy is first you get the data, then you do the feature extraction, and, then you get started with your algorithm. So feature extraction is a very simple concept which may seem complex at first. So let's now take an example. Let's try to predict who will win a particular cricket match using machine learning, right? So now in this data set of first innings, you are just given the opponent who Sri Lanka played against, the wickets, the number of overs played, and the year. So now you have to predict what is the probability or the chance of Sri Lanka winning against one of these opponents in a new match, right? But this information isn't enough. This is where you use the concept of feature engineering. So it's like, now if you're going to predict, if you have to predict who's going to win, you need more information. There are observable factors like, the run, maybe the average run rate, or the pitch condition, whether it's a bowling pitch or a batting pitch. So these factors which you try to extract and evaluate, which you try to, use as the key factors to make the decision whether they are whether who's going to win in that match, they are called features. And the same concept is applied even in our daily life. Let's say we are planning whether we have to go out or not, or whether we are trying to predict whether it's going to rain on a particular day. How do you predict it? You go out, you look up, it's dark, then it's getting colder as well, and then you start hearing noise of thunder, and now you're pretty sure it's going to rain. So for you to make that prediction, you needed these pieces of information, like the chillness you felt or the noise of thunder you heard. Those are called features. Features are factors which can influence your prediction. Now, and that's how, classical machine learning work too. But the problem is, in classical machine learning, we have to hand engineer these features. So for the algorithm to work optimally, we'll have to first manually extract these features from a data set and feed it. But this doesn't always work for unstructured data like, images or sequences like text. Now let's try this through a mental exercise, right? Here we have, let's say we have one image, and first one is obvious. This is obvious, it's a lion. But what about this guy? The first time I saw it, I thought it's a Pokemon called Sandshrew. So now when we first see it, we are trying to understand what this is, right? Actually, this is an animal called a pangolin. Now, if I ask you, how are you sure, or how did you come to the conclusion that the animal on the first image is a lion? It's very hard for you to list down a set of features like we spoke earlier. Probably you may say things like, it has a mane, it's kind of like brown in color. You can show previous examples of lions which you saw, but can you numerically quantify what made you choose this is a lion, or what made you decide this is a lion? It's very hard, because our brain knows it's a lion because we've been taught it in the same way. Now we've seen a pangolin for the first time now, right? Let's assume all of us saw it for the first time at least. Now, this is again, it's easier to guess. It's the same. It's the same animal. It's a pangolin, but it's in a totally different shape and structure now. But still, you are able to classify it. So, how are you doing this? So the internal neural networks in your brain have quickly learned the patterns of a pangolin, the unstructured patterns of a pangolin, and now you're able to reuse it again and again. And that's the fundamental concept of neural networks too, of deep learning too, where we try to extract these unstructured patterns from data, and then we try to use it to make classifications and decisions. All right, now let's get into some of the fundamentals of deep learning. Let's start with neurons. So the image on the left is the neurons in the brain, and the image on the right is an artificial neural network. If you see one thing in common, it's that both it's the connectivity. And just like the human brain, neural networks also have these connection between each other, which they can use to communicate and influence the output which we want. For example, in the case of classifying between a healthy brain and a brain tumor from an MRI image, each of these layers will learn, each of the layers in this neural network will learn different features, right? Or for example, let's say you want to identify whether there's a face in an image or not. Each of the layers in this neural network will try to identify different types of features and learn these features automatically without us having to provide it. For example, let's say the first layer learns basic features like lines and contours and so on. And in the next layer, it learns to identify features like eyes and nose. So the goal of the neural network here is to identify whether there is a face or not. And in the final layer, the model completely learns to identify the face as a whole. So how do these networks learn? How do they, when we call training, what do we call as training? This is called a loss function, right? So we'll start from here. So now what you do first is you first give hundreds of images of faces to your, if you have to classify, if your goal is to classify whether there is a face in an image or not. And you try to tune the neural network to classify whether, there is a, whether you label whether for every image, whether there is a face or not. And what your neural network would do is it would output a probability between, 0 to 1 for every image, whether it thinks there is a face in it or not. So if it's like, let's say 0.7, it's pretty confident that there's a face in it. If it's around 0.2, it's pretty, it's saying there's not a face in it. So now what you have to do is, now you have to go back and tell your neural network whether it has took the right decision or not during the training phase, right? For example, if there is a face in an input image and let's say, but the neural network says there is not a face, now you have to go and update the neural network's weights, or which will, that's a concept we'll look at too, but we will have to go ahead and, go back and tell the neural network to, correct itself. So if you really want to tell how bad the model or how bad the neural network performed, you have to measure it. And this equation does simply that. This is the first maths equation I'm introducing, but it's actually pretty simple. It's called mean squared error. And what you're ideally doing is you're trying to subtract, you're trying to get the difference between how confident the model was. For example, if it's like 70% confidence, confident in its output, and you're trying to get the difference between what the ground truth is, which is, usually 1 if we are considering probabilities. Then you subtract it from the, the ground truth, and you square it so that the value doesn't turn negative. And you get an overall score on how good or bad the models or the neural network's prediction was. Okay, now you're done telling the model how crappy it is, right? You have told it that it has made a bad prediction. And initially, when you train neural networks always, when they start out, they are initially bad. But as with people, it's very easy to pinpoint someone and tell they are wrong. But it is very hard to help them correct their mistakes by saying exactly where someone made the mistake. So backpropagation is this idea, or is this concept where we tell the model how to use the output it got from its loss function to update itself and to continuously learn. So backpropagation in itself is it may seem pretty complicated at first if you look at the math, but it is also pretty simple. So what we are trying to do is, our model has a set of weights, right? Weights are, we have a set of parameters which needs to be updated. So in backpropagation, what we try to do is, depending on the output of the loss function, we try to update the small, weights in the neurons, uh, depending on how each neuron affects the output. So ideally, what we try to do is we try to pass that loss value throughout the network to make sure that we can update each neuron effectively, so that in the next pass the neural network becomes more accurate on making the right predictions. Yep, so that is mostly backpropagation. And now we'll go into what happens inside a network, inside a neuron especially. So this is what happens inside a neuron basically. It's not very complex math actually. Inside every neuron, there is something called a weight matrix, where where initially you just have a random number, you just have a set of random numbers, and you add a bias to it, and then you have this sigma icon in the purple box is just a nonlinear function trying to squish the weights between 0 and 1. So now the neuron internally first makes predictions and has an initial random set of weights, and through backpropagation, what we try to do is we try to update these sets of weights, so that every neuron contributes their part to increasing the accuracy of the prediction. Yep, that is basically neural networks in a gist. Okay, now we've understood some of the fundamentals of neural networks, right? Now let's see where we can apply neural networks. Let's starting with computer vision. So depending on the type of data, the type of algorithm we use would also differ. So there are two very common types of unstructured data. First is images, and in deep learning we call this vision data. This includes anything visual, ranging from common pictures to satellite images to MRI, to so on. And it is also one of the most active research areas in AI. So can't we use the same neural network structure we saw in the previous set of slides for images too? Possible, but it will take a lot of compute power, because let's say if we have an image which is of, let's say, 225 by 225 resolution, so in a grid, we would have around 50,000 pixels, meaning the input layer would need to have around 50,000 neurons in its input layer to take in every pixel as input. And this is very expensive in terms of compute, and it would take a very long time to train. So meet the CNN. So this is the convolutional neural network we were talking about early on. So convolutional neural network is again a type of neural network which focuses on extracting in images, extracting important parts of information so that we don't capture every pixel, and we look at it from an overall perspective. And that's how we as humans perceive images too, right? When we look at, let's say, the picture of someone or something, we don't look at each and every individual pixel to, to understand it. We collectively try to use the entire image to process and understand. So the same concept applies here too. So basically what the CNN does is it extracts these important features from images, the structured features, and it helps the neurons, the perceptron neurons on the later layers to learn effectively. Yep. So that is one use case. Another one is language understanding, and especially working with sequential data. So as we saw earlier, sequential data is also a prominent form of data. So for example, let's take text and language as an example. Unlike images, which are more structured, if you consider how we as humans perceive language, it's very sequential, right? So for example, if you want to train a model to predict the next few words in your sentence, your model should be able to understand the previous words in the sentence to make sense. So let's go through an example. So if you use Office 365 or Google Docs, you would have come across this definitely, where you're typing something and all of a sudden Google reads your mind and recommends the next few words, so that you just press tab and it auto completes. It's not mind reading, it's actually deep learning. But the interesting thing about this neural network model we are seeing here is that it can not only generate the next word, but if you look carefully, it can also understand the previous words mentioned. So it understands the context too. So here it's something about, around 50%, 57% of their working time went towards customers, and there someone is worried about the future of. So when the user types F, it predicts depending on the previous context. So in these types of use cases, we use a different type of algorithm called the recurrent neural network. So, it was going all fun for the past 20 to 30 minutes, but now here we are looking at this weird looking diagram with a lot of awkward symbols. So let's look at something simpler. So simply this model, this neural network model, what it's trying to do is to predict the next word given the current word. So let's say you have the input sentence, Lord Voldemort is looking for Harry. Now we know the next word, but for the neural network to understand, it needs to consider all the previous words to predict the next word. So what the model does is, during training, it starts with one word and then tries to predict the next one, and then using the backpropagation concept we saw earlier, it tries to check whether what the the actual previous word was and what it predicted, and then update itself. So over time, it tries to, whenever it has to generate the next word, it considers the entire previous context before generating the next word. Yes, all right. So yeah, all 30 minutes in, and I think we have already gone through a lot of the fundamentals of deep learning. So now I think we can go through some of the new frontiers in deep learning that's upcoming and that's coming up popularly. Okay, generative network. This is actually a very fun area to work in, and I think at Root Code AI also we do a lot of work around this area. So we'll go into how generative networks work, but we'll start with an example first. And creativity is kind of a unique aspect of humans, right? Something we take pride in. It sets our ability apart from many other species. But in the area of creative AI, what we try to do is we try to sort of unify intuitive creativeness with artificial intelligence. So this is actually all AI generated art, and one of our research team worked on generating these artwork from nearly 200,000 images of artists. And how we did it was using something called a generative adversarial network. So it's a long name, but so a generative adversarial network, or a GAN, is basically where there are two models called a generator and a discriminator. And when given a data set, the generator would try to generate samples which closely resemble the data set. For example, if you have an image of paintings like we did, the generator tries to generate sample paintings as possible. And then we have a discriminator. So what the discriminator basically does is it tries to identify whether a given image is a fake image generated by the generator or is an actual image from the data set. So over time, these two models train against each other, and they essentially compete with each other. And over time, the generator learns to generate images that look very similar to the ones in the data set. And when we get to the point where the discriminator cannot identify the difference between a generated image and an actual image from the data set, that means our generator is good and it's generating realistically looking images. All right, another popular frontier in deep learning is AutoML. So one of the most difficult things when building deep neural networks is deciding the architecture and hyperparameters, right? So the architecture is what we saw on earlier, how you can stack different neurons in ways, depending on the data set, whether you're going to use a CNN or an RNN and so on. So AutoML proposes this approach of using neural networks to design neural networks. So the idea is you create this model, or this neural network model, which can essentially train, output, generate different types of neural network architectures and evaluate them on the data set, and then update itself to, so the output of the neural network is another neural network for a specific task until it gets to the optimal performance. So that is also a very, very active research area within deep learning currently. All right. I think we've gotten to the final section of myths, of common deep learning myths. Okay, this is one of my favorite one. A neural network is the best solution for any problem. Totally false. First of all, neural networks are, or deep learning as a whole is not a silver bullet for all AI problems. Sometimes depending on the nature of the problem and the type of data you have, even a classical machine learning solution would do. This is another interesting one. AI, machine learning, and neural networks mean the same thing. They are, like we saw earlier, they are totally different things, and they are subsets of each other. Machine learning is a subset of AI, and deep learning is a subset of machine learning, but they are not the same things. They are different, and we need to be careful when we refer to them as, when we try to refer to them as the same thing. All right. And in comparison to the previous two myths, this is not that popular, but I've heard it. I've heard it commonly also. So the idea, so this myth is that if you have a large enough data set, you should be able to solve any problem with deep learning, right? Just imagine how life would be easy if that was the case. I'll introduce you to a problem that comes in when you have very large data set. It's called overfitting. So overfitting is this interesting concept in machine learning and deep learning, in which your model adopts too much to the data available. For example, in this case, let's say we want to build a classifier or line that separates these X's or crosses from the circles. The model tries to fit exactly the training data without generalizing, right? So what it tries to do is, instead of trying to find this, appropriate fitting curve, which has some errors, but can separate most of the circles from the crosses. It tries to fit exactly your training data set to the point where it performs really well on the training data, but when it comes to the test data, it messes up completely. This is a common problem when you have so much of data, when you have a high volume of data, but your architecture, your neural network architecture isn't formed properly. All right, I think if the explanation wasn't enough, I think this would be a good finishing for that. Right. This is, I think, another one of the most funniest myths around, where it's assumed that a neural network can learn on its own after being deployed. A neural network can, learn and update its parameters only when it's learned. So, after unicorn and fairies, neural networks which learn in production by themselves don't exist. You either have to automate the entire training process, or you have to train your neural network with new data manually. All right, I think we are mostly done. And I think if you are someone interested in deep learning, there has never been a better time to get into it than now. I think a few years back, it was only a research area, and now even at Root Code AI, it powers most of the products and solutions we built. Yep, I think we have a few minutes for questions then.
So, ladies and gentlemen, you are now free to ask your questions with regard to the session conducted by posting your questions in the Slido platform, whose link is in the Zoom chat. So let's begin with the first question. So question number one for you, sir. Why MSE cannot be used for binary classification problem?
Okay, that's an interesting question. I think mean squared error is depending on what type of data, I think the answer would also differ, but I'll try to be as general as possible. Mean squared error is generally one of the basic loss functions or like error mechanisms used, because what it basically does is it tries to compute the distance between the predicted output. Let's say your probability is 0.7, and let's say the ground truth, which is like 1. I think technically it still can be used for binary classification use cases, but I'm not sure is there any specific type of data, because if it's something like, let's say, if it's something involving sequences of text, then it may be a problem. But MSE can be used, but usually it's not used because it gives performance issues when training the network usually.
Right. So our next question for you, sir, is if I do want to begin my journey in deep learning, what would be my starting point and what courses should I follow?
All right. Okay, that's a great question. Okay, I think first thing I would say not to do is to watch NumPy videos. Don't go through those videos. It's pain. So what I would recommend for someone to start is, or what sort of deep learning projects is, first try Kaggle. And I think Kaggle has a set of, there's the Titanic data set, and there are a few beginner projects with a lot of community support behind. So yeah, that would be, I think, the best place to start as a beginner. And one thing I would say is also to diversify the type of projects you work, to not only go into, let's say, computer vision or image related projects, but also, try out different projects in things like, NLP and time series and so on. So do more projects. You can start with somewhere like Kaggle, and then, but try to find an area of interest within deep learning, like, let's say, computer vision or sequential data, and then pick projects on that topic and go in.
Yeah. So speaking of projects, there's another question. What
Yeah.
sort of deep learning projects can be started as a beginner?
What sort of deep learning projects? Okay. I think as a beginner, I would say a classification project would be easier to start with. There are things like I think MNIST is the default one you can go for, but I think there are a lot of data sets available. And after you understood how classification and how probabilities and some of the basic concepts work, I think you can then go into you can then move into something like machine translation, which is a bit more complex. So that trajectory would be good.
Okay. So our next question for you, sir, is what would be the demand that we would have in the future for deep learning, and what would be the requirement in the job market?
Okay, okay, that's a good question again. um, Demand. Okay, that's an interesting question. I think deep learning as a concept is becoming very important for data scientists and machine learning engineers, as time goes by. And I think deep learning would also become more important, in the toolbox of a data scientist or machine learning engineer, along with a lot of other things like basic data science skills. So to answer the first part of the question, I think there would be a lot of demand for knowing deep learning concepts if you're someone who wants to be a data scientist or machine learning engineer. What would be the requirement in the job market in the future? I think uh, currently, if we take the whole scope of data scientists and machine learning engineers, there is very high demand. Even we are recruiting very aggressively. We have internships open too. Uh, there is a very high demand for data scientists and MLEs. But for deep learning specific roles, I think there are only research vacancies mostly available. Because if you're a data scientist, deep learning wouldn't be the only thing you're working on. So there's still not something called the deep learning engineer. It's either a data scientist or machine learning engineer. So yeah, I think given that context, if you're asking for the demand of a data scientist, it's gonna be high. And yeah, deep learning as a concept is now very much in demand to know too.
Okay. So we actually have a lot of questions. So I
Oh
hope you'll
yeah.
answer. So what kind of performance of hardware do we need to perform a deep learning establishment?
Okay. Okay. Uh, I'm not sure who asked the question, but when you mean deep learning establishment, what do you mean? Do you mean, is it something like, okay, that's a weird question. What kind of performance of hardware? Okay, let's try to see it as what kind of hardware is needed to train deep learning models. Um, I think currently you can use, if you're like starting out, you can use something like Collab, or if you have a GPU powered machine, you can use that too. But in terms of large scale hardware, we use in industry, we use things like GPUs or GPU clusters, or even some cases TPUs, tensor processing units, for training deep learning models. So yeah, hope I answered the question.
Okay. Next up, what kind of network would you prefer? A shallow network or a deep network for voice recognition?
Okay, I think voice recognition, it's got to be a deep network, because a shallow network wouldn't work unless you are doing a really huge amount of pre-processing and feature extraction. So usually for very unstructured tasks like voice recognition, it's good to go with deep neural networks.
Next question. Let's say we have to build a neural network architecture. How will you decide how many neurons and hidden layers are needed for the network?
Okay, so it all depends on the data, right? So and it depends on a variety of factors. I think the major factor is what's the type of data you're working with and what's the size of the data set you have. So and that leads to how we decide, how many neurons or how many hidden layers are there, or even what type of algorithms you're going to use, like CNNs or RNNs or LSTMs, or within the spectrum of whatever we have available. So how will we decide how many neurons? It's totally depending on the data set. Let's say we have a huge amount of, let's say we are working with around, let's say 200,000 or 300,000 images on a classification task. Then we'll have, very deep networks with sometimes even pre-trained layers. Uh, so yeah, but again, that is even in, I think many popular researchers say that it's kind of like an art sometimes than a science. You have to experiment and see. Yeah, so usually it's fully dependent on the data, and you need to check things like whether overfitting is happening, and if so, then you may have to reduce the size of the network, or reduce the number of hidden layers and so on, or use concepts like attention, and so on. So yeah, I would say that's like the fundamental framework of thinking to decide how when designing an architecture.
Right. So next up, why CNN is preferred over ANN for image classification tasks, even though it's possible to solve image classification using ANN?
Okay, so the problem is, now let's say if you take an image, an image is simply a grid, right? If you consider an image, it's simply a set of pixels. And for the computer or for an algorithm, a pixel is simply a value between 0 to 255, right? If it's a color image, because of the RGB scale, or if it's a black and white image, it's 0 to, let's say, between 0 to 1. Now, if you have, let's say, a 225 by 225 image, then if you will have around 50,000 pixels. So when you have 50,000 pixels and when you feed it into a classical ANN, a set of classical ANNs, one thing is you need to have 50,000 input neurons, right? And when you have 50,000 input neurons, you're nearly absorbing every information from every pixel into your network, and you're training it. So first problem that comes up is the compute power. So even if you have to train with like 100 images, you're going to use a lot of compute power to do that. Second problem comes in is when your network is training, it's looking at every pixel individually, right? But ideally what we want to do is, what a CNN does is, it tries to identify particular regions which actually matter to the prediction, and then use them to tune the network. So that's mostly the reason. One thing is, it will be very noisy for the network to just use the raw pixels. Second thing is, convolutions help us a lot by extracting important features from the image autonomously. So that's why CNNs are better candidate for images than ANNs.
So, sir, are there available internship opportunities in this field in your company?
Oh yes, yes. I think we are very actively recruiting. I think we have an opening for an internship that's open now. I think if you go to rootcodelabs.com/careers, you should be able to see that and apply. Yeah. So we are very actively recruiting for internships now.
Can you build deep learning models based solely on linear regression?
Okay. Linear regression is a different concept. I think the equation we saw, right? How a neuron works, the Wx plus b, the weight matrix times the input plus the bias, and you have the whole activation function. Uh, that so a logistic regression model is like one neuron. Um, so the concept of deep learning is stacking these layers of neurons in a way that they learn the underlying patterns in unstructured data, right? So technically it's not possible to build deep learning models based on linear regression. Linear regression is a machine learning based approach.
So other than data augmentation, what are the best ways to improve the accuracy of the model?
Yeah, I think data augmentation is a really good way because it increases the size and the diversity of the data set. Other than data augmentation, different ways include trying different architectures. For example, if you're working with text data, you can experiment with starting from RNNs are the basic sequential algorithms. You can experiment with things like LSTMs or transformers and or attention models and so on. So trying out different architectures plays a big role. Other than that, you need to also make sure that overfitting doesn't happen. So you can use things like L1, L2 regularization or dropout. Those are also methods to potentially improve accuracy. And yeah, I think and also tuning the hyperparameters also play a big role. For example, things like the learning rate. Which decide how gradient descent happens when you're doing back propagation. uh, how sensitive your model is when optimizing the loss curve. So yeah, factors like those mostly. So just to point out, hyperparameters, regularization, and testing different architectures.
Right. Okay, a few more. So are there any problems when using batch normalization in deep neural networks?
Okay. Batch normalization is usually, I think it's usually a training optimization done. Um there aren't any problems when using batch normalization, but sometimes if you have memory constraints, doing batch normalization as a prior step can become an issue. But generally, there is no problem you doing batch normalization when training network. Generally, it's considered a good practice.
Okay. Next question. Any government agencies currently using deep learning? What are the potential uses for deep learning in government entities?
Okay. I think European governments in Asia, I'm not pretty sure, but some European or Scandinavian governments are using deep learning. For example, Estonia is a really good example. I think um, we have an office in Estonia too, but I've heard they use deep learning a lot in things like conversational AI. So yeah.
Okay. I think will be the last question. What are the opportunities to do master degree in foreign with the relevant field? I think she means the
Deep learning.
yeah, foreign degrees in like masters. Is there a good option? If so, are there any scholarships or any other options?
Um, Honestly, I'm not exactly sure of the master's degree programs in deep learning, but I think if you would I think currently every data science or computer science master's program, you can specialize your research in deep learning. That's what I did too. Um, yeah, so but deep learning, I think abroad, like, outside of Sri Lanka, I think it doesn't usually go as like MSc in deep learning. There may be some, but if you do an MSc in AI or computer science, you can specialize your research in deep learning. Scholarships, I'm not exactly sure. I think we'll have to search for that.
Okay, thank you so much, sir. And with that, ladies and gentlemen, we shall conclude our questionnaire session and the second workshop as well. If you do have any more questions, you may direct them to our Facebook page. So I would like to thank Mr. Thirunayan for taking his time to come and join this evening for our second session in the workshop series. And I hope his knowledge has helped all of our young participants gain so much needed academic additions. I would also like to thank him for managing the time allocated to him very well. So thank you again, thank you so once again for your most valuable time. And as a gesture of thanks, I would like to present our speaker with the token of appreciation. So thank you, sir, once again for joining the session.
Thank you, Nipun. Thank you, guys.
So now I would like to request everyone to turn on their video cams for a group photograph. I totally understand that most people have power cuts these days, but if you don't, and if you're in the position to do so, you may turn on your cam for a group photo. We shall give a couple of minutes. So a kind reminder to turn on your cams if you are in the position to do so. We'll be taking a group photograph in just a few moments. Okay, so I guess we're ready to take the pictures. So in 3, 2, 1. Okay, I would like to thank the participants who were able to turn on the cams for the group photograph. So yeah, a huge thank you to all our participants for joining us in this session. We hope you gained some much needed knowledge, and we hope you thoroughly enjoyed the session as much as I did. So also, we are hoping to see you all in the next iteration of the pre-bootcamp series next week, which will be about the applications of artificial intelligence. So goodbye for now and take care.
See you guys. Thank you.